Hi, welcome to this talk on Ragdoll authoring improvements in O3DE. I'm Dave Greer. I'm a senior engineer with the Game Engine and Developer Services team at AWS. To begin with, I'll just do a quick overview of what's going to be covered in this talk today. I'll start out by giving a brief description of what I mean when I talk about ragdolls, in case you're not familiar with the term already. Then I'm going to do a run through of setting up the physical representation of the character in the animation editor, highlighting the recent improvements we've made there. I'll talk a little bit about the technical background to some of the automatic setup features that have been added, and then I'll finish up by talking about some ideas for future improvements to the Ragdoll authoring workflow. Just want to highlight that one thing I'm not going to cover is how to add a ragdoll to an animation graph. Ragdolls are physical representations of characters, which are frequently used for character death or when a character becomes unconscious. This is an example from a game we made for a game jam last year. In order to be able to simulate a ragdoll, there are a couple of aspects of physics configuration that we need to set up. The first one is collision geometry, which we want to attach to some of the bones in the actor. So for example, we've got these capsule colliders here on the arm joints. And then the second thing that we need is joint limits, which are attached to each joint, and they control the range of motion that is allowed in the physical simulation for that joint. So that prevents you from getting into unrealistic configurations, like the elbow bending backwards, for example. So just to demo how you can go about setting these things up, I'm going to clear the existing definitions so I can start again from scratch. Cool. So so now we want to select some joints to add to the ragdoll. So one thing that we've added recently here, which makes life easier, is picking in the animation editor. So you can just click on a bone to select it. So now I've got the left wrist selected. If I right-click and do Add to Ragdoll, that's now part of the ragdoll. It's also added the wrist's parent bone and its parent bone and so on all the way up the chain to the root. The reason we do that is that we always want to have the root in the ragdoll, and we don't currently allow skipping any joints in the ragdoll compared to the animation skeleton. It's possible we may relax that restraint in the future, but right now you can't skip any joints. And the reason for doing it bottom upwards rather than top down is to avoid adding a lot of small bones. Like for example, if you look at the wrist, underneath that there's all these child bones which are quite small and wouldn't really add a lot to the ragdoll fidelity, but do increase the computational cost of simulating the ragdoll. So we want to avoid including those, and that's why we go bottom up from the wrist. That bottom up selection means that it is quite easy to gather all the joints that you want added to the ragdolls. You can just click on a few end effectors and add them to the ragdoll. So if I do that with the other wrist and the feet, and the head, okay, so now I've got all the joints that I want added to my ragdoll. Whenever you add a joint, it automatically adds a collider with an initial guess at the geometry that would be most suitable. The way that it figures that out, if I look at this joint for example, it finds the direction of the bone and makes that the long axis of the capsule, and then it looks at the vertices in the skinned mesh which are most closely influenced by this bone, and it uses the spatial distribution of those vertices to compute an estimate for the radius for this capsule. So capsule colliders are added by default, but you can also use boxes and spheres, so I can remove that capsule and add a box if I decided that box would be a better choice for the geometry. But yeah, I'm just going to go back to capsule. So that auto fitting that I talked about, it usually does a pretty good job, but you can see there's a problem here with the upper legs. These two colliders are highlighted in red, and the reason they're shown in red is that they're intersecting, which would cause a problem when you simulate the ragdoll, because the physics simulation is going to try to depenetrate them. It's going to try and push them apart, but the joints of the ragdoll are trying to hold everything together. So those two competing forces will lead the simulation to be unstable. So we want to resize those colliders to avoid them intersecting. The animation editor was recently updated to use an atom rendering viewport, which gives us access to features such as manipulators and viewport cluster UI. So you can see there's a new viewport cluster up here, which allows you to select tools to manipulate the colliders. So you can see I can select the dimension manipulator and then just resize this collider, and you can see that it's no longer red because they're not colliding anymore. There's also translation manipulators and rotation. So for example, I could resize this collider to make it align a bit better with the torso of the character. Cool, so now I'm fairly happy with my collider setup. The next thing I want to do is set up the joint limits. So one thing that we've added here, which makes life a whole lot easier, is automatic joint limit setup based on poses sampled from a motion set. So if I load, I just need to make sure I've got a motion set loaded here. This is going to be to allow the automatic fit system to sample poses from these animations in order to figure out the range of motion that each joint should have. And then if we go back to the physics setup and turn on the joint limit visualization. Okay, so now all I need to do is click on this button, and it will go and look at a whole bunch of poses from that motion set, examine the kind of range of motion that is exhibited by those poses, and then compute a limit cone which will encapsulate all of those poses but minimize the volume of the cone, and it uses a nonlinear solver to do that, which I'm going to talk about in more detail later on. So yeah, I can set up all of these joints quite easily. You can see it's automatically figured out a limit for the elbow, which makes sense because it is going to allow the elbow to straighten out but not bend any further than that. Like the knee is another good example of the kind of constraints that we want to apply to that joint so that it doesn't get into unnatural configurations. So yeah, that makes it really easy to set up joint limits. If you do want to do any minor tweaks, there's also joint limit manipulators that allow you to rotate the limit cone, or you can resize the limits if you want to make them wider. And then there's also manipulators for the twist limit as well. So I could make that a bit tighter, for example. So this is a representation of how the joint limit automatic fitting works. You can see each of these lines represents a pose sampled from the motion set, and overall they form a kind of cloud, which we then fit a cone to. And there's two objectives with the cone fitting. One is to try to include all of those lines inside the cone, and the second is to try to make the cone as small as possible so that it only just encapsulates the example poses. In order to perform the optimization for the joint limit fitting, we use a nonlinear solver called BFGS, which is short for Broyden, Fletcher, Goldfarb, Shano. I'm going to give a very brief overview of how that works here. If you're interested in a more detailed description, a textbook like Numerical Optimization by Nossadal and Wright would be a good place to go. So the basis for how BFGS works is Newton's method, which is an iterative algorithm for finding zeros of functions. And the basic idea is actually fairly straightforward. You start out with an initial estimate of the x value, which is going to give you the function evaluating to 0. So in this kind of toy example here, we're starting out with the guess x equals 3, which is represented by the red circle in the graph. And you can see the value of f there is like 60 something. The way the method proceeds is basically to look at the gradient of the function at that point and kind of extrapolate downwards towards 0 and use that to construct a new estimate for the value of x that will give you the 0 for the function. So that's represented by the green circle on the x-axis. And you can see in this case it's you're getting closer to the actual 0 of the function, which is at x equals 2. So on the right is just writing out a formula for what I just described in words. So the gradient is just the value of the function divided by the difference between the current estimate of the root and the updated estimate. And if you just rearrange that formula, you can get a formula for the next estimate based on the current estimate and the value and gradient of the function at the current estimate. And yeah, I mentioned it was an iterative technique, so you can kind of continue that process and kind of start again from the green point and repeat the process, and you get an even better estimate. And after a few iterations, you're getting very close to the root. So Newton's method has this property called quadratic convergence, which basically means that it converges very quickly when it's near the root. And you can see in this example the number of decimal places in the estimate which is correct is roughly doubling with each iteration. That's what quadratic convergence means. So it's very rapid convergence once you get near to a solution. So far I've just been talking about finding zeros of functions, and we actually want to find a minimum of the objective function, and that corresponds to a 0 in the first derivative. So we need to go through the original equation and replace f with its first derivative. And then also, so far I've only discussed one-dimensional examples, but most of the interesting cases are going to be higher dimensions, and basically you wind up replacing the first derivative with the gradient, which is a vector of first derivatives with respect to each independent variable, and then instead of dividing by the second derivative, you need to inverse multiply by what's called the Hessian matrix, which is a matrix of second derivatives. So that matrix of second derivatives is very expensive to compute because very often you're figuring out the derivatives using finite differences, and if you need to find second derivatives, that's a lot of work. So the basic idea in the BFGS algorithm is to replace replace that expensive Hessian matrix with an approximation which is just based on first derivatives, which are a lot easier to compute. Don't need to worry about the details of the equation here. It's just for completeness. But the point is that this is a simpler approximation to the second derivative part. Now I mentioned that Newton's method has very rapid convergence near the solution, but what if you're not quite so close to the solution yet? And there's a danger here that you can overshoot if your gradient is basically pushing you to go beyond where the zero occurs. And this is a kind of pathological example here, but you can see the gradient at the first iteration is enough to cause the second estimate to be further away from the solution, and then after that it kind of blows up. So in order to avoid that kind of scenario, a very common strategy is to use something called a line search, so basically the idea here is you find a direction to search in, that's what Pn is, and that will be determined as before using the Newton method, but then you multiply that by a step size alpha, which means that if in the situation where you might have overshot, you can make sure that you take a smaller step and avoid that kind of catastrophic behavior we saw in the previous slide. There's a set of criteria called the Wolf conditions, which it can be shown are sufficient to guarantee that the algorithm will converge. There's a lot more detail about this in the textbook I recommended earlier, but just to summarize, there's basically two parts to the Wolf conditions. The first is that in order to accept a value of alpha, the step size, we want the objective function at that position to have improved compared to our current value by an amount which scales with the size of the step. So basically you want it to be below this dashed line here. And I've highlighted in green the kind of regions which are acceptable on the basis of that condition. And then the second condition is related to the curvature of the function at that point. So you basically want the slope to be above, like greater than this other dashed line in order to accept it, because otherwise you're basically taking a step size which is too small, and you could do better by increasing your step size. So those are the Wolf conditions which, if you're able to satisfy those, then the algorithm is guaranteed to converge. And there's some pseudo code here. I wouldn't worry about the details, but it's just to illustrate that there's a procedure you can follow which will make sure that you meet those criteria, the Wolf conditions, and so you'll be able to make progress towards the solution. So that's an extremely brief overview of how BFGS works. In terms of implementation, we looked for an existing third-party library, but we ran into problems with licensing. A lot of the existing packages depend on Eigen for linear algebra, and Eigen it's a great package, but the license unfortunately is not MIT or Apache, which is kind of what we'd want to be compatible with O3DE. So if anyone's aware of a package that does have a suitable license, please let me know. But in the meantime, we implemented a basic version of BFGS ourselves. It currently lives inside the PhysX gem, because that's principally where it's been used so far. But if any other applications arise, it would be easy enough to move it to another location. It does have good coverage in terms of unit tests, and you can see the coverage numbers here. So we've got good faith that it's a robust implementation. In terms of how to actually use the solver, it's actually quite straightforward. That you basically only need to implement a couple of functions. One is at the bottom we've got the get dimension one here, so that's basically telling the solver what the dimension of the problem that it needs to solve is. In this case, this example is for the joint limit optimization, and here we basically have a quaternion which describes the orientation of the limit cone. So that's 4 degrees of freedom, and then there's 2 swing limits in the y direction and the z direction, so that's another 2. So there's a total of 6 variables which kind of describe the optimization problem. And then you need to implement the objective function. And as I mentioned earlier, there's basically 2 terms in the objective function for the joint limits. One, the first one, it's trying to avoid the example posers going too far outside the limit cone. And then the other one is a volume term, so it wants to minimize the size of the cone, because otherwise if you could trivially satisfy the first objective by just making a huge cone, but then it wouldn't be very much use as a joint limit because it wouldn't be preventing any implausible posers. The same solver is also used in the asset pipeline to fit primitive colliders to meshes in order to use them in the physics simulation. Optimization is a very powerful tool, and we've only kind of scratched the surface of what might be possible with it. So if you have any ideas for ways we could apply this, I'd be very interested in hearing from you. We've made a lot of great improvements to the Ragdoll authoring workflow recently, but we still aren't done. This video shows a lot of ideas that we've prototyped but haven't made it to production just yet. So for example, the small bone detection, as I was talking about earlier, you generally don't want to include bones like the fingers in the ragdoll, and you can detect those automatically by looking at the volume of the mesh that those bones influence compared to their parent bones. Also improved collider generation, so taking the initial estimates which I described earlier, and then you can use the BFGS solver to improve those estimates. Also symmetry detection, so figuring out the kind of left-right symmetry of the character and ensuring that any colliders on bones along the central axis are symmetrical. And also self-collision resolution, so automatically, as I mentioned earlier, the colliders which are kind of interpenetrating are currently highlighted in red, and you need to manually adjust those to prevent the self-collision, but there are ways we've prototyped to automatically resolve that situation. And a lot of other ideas as well which aren't covered in this video. And on top of that, if you have any suggestions on how to improve the Ragdoll authoring workflow, or if you'd like to get involved in the coding side, definitely like to hear from you. Or if you've got any ideas how we can exploit the optimization functionality that we now have. Cool, I'm going to wrap up there. To summarize, I demoed the setup process for the Ragdoll in highlighting the improvements we've made recently. I also briefly outlined the BFGS solver and hopefully convince you of the power of optimization as a tool. And I briefly ran through some ideas for the future direction for Ragdoll authoring. You can find me on GitHub or in the SIG Simulation Discord if you'd like to give any